وصلت بعد دقيقتين خشيت. الحمد لله يعني هذا استهلك الوقت بشكل.
سويته معاه
ايه كان بيحط لك اشياء تصميم وزوايا ليفل عالي. امس السبت قبل امس السبت قعدنا لين الساعه 11 في الليل. اليوم اللي قبله لين 9 في الليل على هذا.
وعندك شغل بالبرنامج اليوم؟
عليكم السلام ورحمة الله. أخبارك إيه يا سيد؟ Enjoy it.
Excellent. Appreciate your honor to have you.
ممكن قصة.
That's okay.
اوكي تطلع. يمكن 10 خط واحد يحتاج. You're going to have and your life
Thank you very
سياسة استدعاء وشوف اجتهاد الله ما
الحمد لله. كيف حالك أبو محمد؟ أخبارك إيه؟ الحمد لله. كيفك في أي ديبارتمنت؟
راس النور.
راس النور.
ديبارتمنت هو سبورت ديبارتمنت لو مانيفاكتشرنج سبورت.
طيب إن شاء الله مبسوط الشغل.
الحمد لله هو مشابه جدا للسي سي لا تعرف.
نعم وصلت السيلز ديبارتمنت.
But related to the refineries also.
طيب إن شاء الله.
الحمد لله.
وانس بقى تتكلم عن الاكسبيرينس بتاعتك في واحد من السيمينارز دول. واحد من السيمينارز تتكلم بقى الشباب عن فترة الدراسة اتس اوكي. يعني انا قصدي النقلة عن هاو تو ميك ا ديفرنس قد ايه الكورس
السلام عليكم ورحمة الله
كان ليه علاقة.
On behalf of KVB ASME and Mechanical Engineering Club, I would like to welcome you all to our seminar today. The title of today's seminar is Introduction to Steam Turbine, and we would like to welcome Mr. Biki, who will present our subject today. Mr. Biki is currently working with Saudi Aramco Global Manufacturing Support Department as an experienced machinery engineer with more than 20 years of experience in this field. Furthermore, Mr. Biki has worked for Chevron Social and Astron Energy engineering project related to air blower steam turbine. And now I will leave the floor to Mr. Biki.
Thank you very much. Thank you. Good evening, everybody. It's an honor to have you this evening, where we're gonna utilize this time to exchange knowledge. That's the whole idea. Whatever we've learned over the years, we would like to use this evening, this platform, and share with our future engineers. So before I go into a detailed presentation, I think I can just quickly recap. I'm currently working for Saudi Aramco Global Manufacturing Support Department. I am focusing on rotating equipment or turbo machinery on the reliability side and any challenges or field issues related to rotating equipment. Okay, so we'll go ahead. So the whole idea is I encourage the interactive session. So if there is a question or there's something that you want me to clarify, feel free to raise your hand and we can we really need to make this a very practical interacting. Of course, we have to manage the time as well. Is the voice clear? Everything okay so far?
Yeah.
Thank you very much. Okay, so we're going to take you through quickly a journey of steam turbine. We'll share with you how the steam turbines came about. We will go through the working principle. Nothing will be intimidating for all of us with working principle. And really the spinal cord behind it is the knowledge of thermodynamics or thermofluids. We will look at the components, what sort of components, let's complete the whole thing and then you call it a steam turbine. We will look at the classification, in industry, how do we classify a steam turbine? It will also be relevant in the thermofluids, nothing will be really strange. We will look at then under classification, we'll look at the stages, compounding, the blading, exhaust conditioning, the governance system, I'll cover that. We will look at a very interesting section for all of us, which is performance. It's also very important in the industry, steam turbine performance. And then we'll do the skid. The idea with the skid is to give the future engineers an idea that when you walk in a facility and you go past the steam turbine, how it look like in general. And then I will share with you the challenges we are currently in the field facing with steam turbine reliability issues, performance challenges. I'll cover that quickly with you. And then we will look at quickly, really the last part before Q&A is just to give you a taste. How can you select between an electrical driver or versus a steam turbine? What sort of decision metrics you can use? This is just to give you a flavor. It's not in detail, but it's to give you a feel. Then we will open the floor for a Q&A session. Then we can exchange and continue exchange knowledge. All right, we cover a bit of a history of the steam turbine. This steam turbine is what I'm looking at the picture on the right. Who can tell me what is this steam turbine used for? Who can just give a guess now? What is this steam turbine used for? What you see on the right hand side? Okay, so the steam turbine really is the real answer. This is a toy. This was a toy created by the gentleman Alexander. So he invested this. This never went into a commercial market. So that was just an idea. He was trying to come up with an idea to come up with the steam turbine. So the short answer, what you see on my right hand side, you are seeing a toy. Okay, very quickly, 1672, the way steam turbine started to become known, and one was developed for the passenger car. 1775, the first reaction turbine. I'll cover late what is the reaction turbine. The first one was available. 1807, we get to know there was one available that was used to drive a fire pump. Compound turbine in 1827. Marine industry as well was lagging behind. 1854 they came in. Nuclear came in. Electric drive or production was in between marine and the nuclear industry. Then the locomotive trains, locomotive train 1929, they came in. They were able also to have a locomotive driven by steam turbine. This is just the milestone, the journey for steam turbine. Who can give me a very quick answer? How does the steam turbine work? What do you think? How does it work? I mean, we are making an interactive section, so this is a start. Give it a try. There's no wrong or right answer. Yes?
Converting the power of the steam, which is a pressure and velocity, into a mechanical power.
To a mechanical power. You have your hand up as well?
Using the difference between pressure to rotate creating difference in pressure
Yes, saying it loud. What is it used for?
to rotate the shaft.
To rotate the shaft. Okay. The last person want to give it a try?
Exchange
fluid to produce work.
Change the angular momentum to exchange? Okay. All right, we're gonna limit this one for 3 people. There's more coming, but I think if I listen to the 3 gentlemen, I will hand over a chocolate to him. He stated very well. Please hand over a chocolate to him. Okay, I did mention the work principle. So what you all see now, nothing strange. This is a concept we're all familiar with. So I have a theoretical ranking cycle on the left-hand side, and I have a modified cycle on the right-hand side. Before I go into cycles, I will re-emphasize this explanation of how does the turbine work. Steam turbine utilizes high energy of the steam, and it converts it into a mechanical energy. Keep note of this definition. It's a very important core definition. It's going to keep coming again in any form. Later it's going to come in a form of calculation. This is a very important definition. It utilizes the energy of the steam. Rankine cycle we're all familiar with. So boiler state 2 to 3, that's the heat added in to produce the steam. There is a component that is going to consume the steam at state 3 and 4, which is the steam turbine in this case. When the energy has lost its content or its value, we then condenses the steam. But because the steam is already clean, we don't throw it away. We return it to a condenser, we return back to a feed pump. We then add energy to the liquid and we bring it into the boiler, so the boiler doesn't work hard to regenerate the steam. Then it remains a loop, it remains a cycle. Then if you look at the other one on the right-hand side, so the demand and the need of energy is changing, so the cycle is accommodating the changes. We now added the turbine now called low pressure turbine. So it means the HP turbine, high pressure, will take a steam at a very high temperature and high pressure from the boiler. We will do work with the turbine, but we will not return the steam to the next turbine to drop it down. We'll return the steam back to the boiler, we reheat it, then we bring it back to the low pressure turbine. We are improving now the cycle efficiency, and again the condenser comes in, the boiler feed water pumps helps us again to bring the liquid back into the boiler. At the bottom, I think you're all familiar with the equations. So the pump is not related with the heat in the cycle, but the pump is adding energy on the condensate, and the boiler is not related to any work. The boiler is just helping us now to raise the steam pressure and the steam temperature. The turbine has nothing to do with heat. A turbine is hungry for something. What is that something? That is a high pressure steam and a high temperature steam, so that it can give us a torque. We need that torque for something else. That is the function of a steam turbine. The condenser has got nothing to do with the work. It helps us then the heat, evacuate the heat and retain the condensate. It's like a heat sink, a heat transfer. Then we return the condensate. Boiler feed does the same. Then the boiler doesn't have always work with the cold, saturated water to make the steam. Then we are now helping the boiler to work a little bit more efficient. Any questions so far? Again, this is called fundamental. If any engineer missed this concept, you've missed the steam turbine. If any engineer mastered this concept, you've got the steam turbine. Nobody can tell you anything about the steam turbine. You become a design engineer in the future, you've got the foundation. Okay, Shabab, let's share the conversation. There is another question on the board. The application, where do you think this steam turbine is used? So we start there.
Produce electricity.
So in the electrical application, it is relevant. How does it produce electricity?
Change the motor receive the work. Change it to electricity.
The motor receives the work from where?
From the turbine.
Okay, good. And any other one want to try? We're going to limit to 2 for this one. Yeah.
Single stage turbines used in the industry or the plants as an alternative to motor.
As a?
Alternative to the motors.
Excellent. Both answers are very correct. Give them chocolate. They cover it very well. I cannot falter them. They got the fundamental definition of a steam turbine and ways it applied. That is correct. Okay. Right, we're still on the working principle. I won't be long here. So it is used as a prime mover because the gentleman started by saying there is a mechanical energy available in the shaft of the steam turbine. So we take advantage then of this mechanical energy he was talking about. We're then able to drive a centrifugal pump. We can also drive a compressor. We can then drive a generator. Now, depending where is the steam turbine used, is it for power purposes, is to propel the ship, is a nuclear boiler system, or is a gas compressor. So now a steam turbine provides an option because the mechanical torque or the mechanical energy is available. It's just, so what you see in the picture is just an open, cutout drawing. So these are the steam turbine blades, and we are driving, you all familiar, this is the impeller, this is a centrifugal pump. Later I will cover this in detail, do not panic, I'll get there to the component. Again, if I won't be long, I think we all got down the principle. So I'm just showing another process flow diagram, how the steam turbine receives the steam from the boiler. In industry, we say it's coming from high pressure steam header because the source of this high pressure is a boiler. Then we channel the steam into the turbine. To get the steam, we have to go through the inlet valve. We've got the control valve. We've got the trip valve. Then we've got a nozzle. This nozzle, later you will get the knowledge what it does. I'm sure you more or less got an idea. Why I'm showing this, I just want to cover these three valves quickly before I go to a low pressure side. I want to cover quickly with you the high pressure side. So the valve you see, the first valve you see, inlet valve, is normally we can use during maintenance if we want to isolate the steam turbine. But when you see the next two valves, the one in the middle, we now use it to load or unload the steam turbine. There can be a case where demand of the torque that you talk about is not needed. So what we do is we tell a turbine, look, the demand is low, please reduce the steam consumption. It's such a flexible driver that we can regulate the steam consumption using the control valve. The next valve, it's a no-go. It says trip valve. What it means is, if I put it another way, I'll explain later. Think of a steam turbine as a crocodile. A steam turbine in industry can be a crocodile because most of them, they run at a quite high speed, and if the speed gets out of control, you need to run away from the steam turbine because a disaster could be in a minute or a second. So that valve, that design of that valve is very important because that valve, when it sees that the turbine is now not controlled in terms of the speed, it can now immediately shut off the steam. So normally design engineers make sure that that valve is almost on the chest, on the body of the turbine, so that the volume of the steam can be immediately cut down and it shut the steam completely, so we kill the torque. All we are doing, we kill the torque, then we kill the speed. That is how we stop a steam turbine. Normally, we do not want to stop a turbine in this way, but this is an emergency when we are failing to get the turbine back into control. This is our last line of defense. In general, I'll cover later how do we stop it normally under control condition. A decision is made, please stop a turbine. There's a way to stop it properly, but that valve I'm explaining is for safety reason.
Is the control valve an electrical instrument or mechanical?
That's a good question. Okay, this valve is normally linked with instrumentation. Very intelligent algorithm software because it's in milliseconds it must stop the steam. The moment it gets activated, that's its job. But when the turbine is still under control, that valve is fully open, turbine is happy, is receiving the steam as normal. It does no control on the steam. The owner of the control, this one load and unload the turbine. That's why it's called a control valve.
When we pump the fluid, the steam, and we get it to the turbine and the control valve decrease the amount of steam, isn't that a waste of energy?
Okay, so there is a steam available on the head of the valve. There's a mechanical valve fully open, but here we want to regulate the load. You cannot always think of a waste of, it's not a waste, it's still in a closed loop. All what we're doing is we are using an energy according to the demand. This is an advantage a turbine is giving it to us. We are not wasting the steam, but we are telling a boiler we do not want X number of ton of steam at that pressure. We need a little bit lower than that because the compressor now maybe requires a lower load or a generator requires, it gives the engineers the flexibility without wasting steam. Okay, we good? Really, that's the reason I want you not to forget the valve. We will get into the component later on. Then when the steam is done, when we extracted the energy from the steam, then we return the steam to a low pressure system. A low pressure system, if you saw the first picture, the principle, we could be then returning the steam to a condenser and then back to the boiler. So this is really a line receiving a low pressure steam. Later, I'll cover all these auxiliaries. What is the function of a steam trap in a steam turbine? And then the nozzle I'll cover also in detail. I'm just giving you a flavor how the steam flow from a boiler to the turbine. Okay. So what do we think? I explained a little bit the steam turbine. We covered the principle. Do I think it's similar to a centrifugal pump? Do they do the same thing? Who want to give it a shot? And when you give an answer, tell me if you say they're similar. Oh, sorry, we have an answer. Okay. I forget you already. We're going to choose right. Yeah, you can go ahead.
The turbines act like a reverse for the pumps. So the turbines take the rotational motion of fluid and put it into rotational motion to the shaft. But in pumps, the reverse is happening. You take the rotational motion of the shaft and transfer it to rotational motion to the fluid.
To the fluid. Okay, hold your thought. The next try. Yes, go ahead.
Turbines deal with the steam and pumps deal with the liquid phase.
But the working principle, do you think?
The reverse.
I want someone who can explain to me how's the reverse. Who can try? I want to understand a little bit more about the reverse. Yeah, go ahead.
Turbine consumes the energy, but pump instead puts more energy by increasing the pressure.
The pump does what?
Increase the energy by increasing the pressure.
It adds energy into the fluid. Thank you very much. I think he deserves a chocolate. He really put it in a thermofluid terms. A steam turbine, it's consuming a steam from the boiler and then it generates energy. The pump does the opposite. The pump puts the energy into the liquid so that we can get to from inlet pressure to a high pressure. Turbine is the reverse. It is extracting energy from the liquid. Yeah, we get it? Oh, I need to click the right answer.
From the laptop.
Oh, from the laptop, sorry. Yeah, we're getting old with the technology. Did it change the color? Right, so they are not similar. I'm just confirming he answered very well from a thermodynamics perspective. Okay, we covered the components. So we did explain this. I'll try and take you through all the components of the steam turbine. So what you see here, we have a shaft. We're already familiar with the rotor, we call a shaft. This is called a disc. Not sure, let me try and see if the laser can work. So you can, oh, sorry. So you can see, okay, it doesn't work on the screen. Let's try this way. This is a shaft. This is a disc. At the periphery of the disc, you got the blades. These are the blades. You will cover them in detail later. You've got a casing where you house the disc. You've got the seals where you prevent the leakage of the steam. Very expensive commodity of energy. We don't want to lose it. We want to contain it within the turbine so we can extract more energy. Then you've got the bearings. We now support the shaft. The bearings have oil. This is a bearing housing. It has oil inside. We don't want the oil to go to the steam. We then put a seal to prevent the oil. We have a seal to prevent the steam. So we have a speed sensor. This is like a gear teeth at the end of the shaft. This is your speed to measure or to monitor the turbine RPM. Why? You saw that, you remember the picture with the red valve. This is important. Any turbine that we operate, it's important to keep track of the speed. And then this is your control valve. This is your trip valve, control valve. We're telling it, this is how much load we now need so that the torque available here can meet the demand. Then I go back quickly to the component. I've covered the seal, the exhaust. So low pressure steam, connect the pipe, we take it back to the condenser. High pressure steam on the other side, that flange, that is called inlet connection. The steam is coming from the boiler. I've covered the bearing, I've covered the trip valve, and then we have a governor. This is a governor valve. Later on, I will go in detail. And then inside here, there's a special device, very important, called the trip pin. Trip pin, I'll cover again how it works. Basically, it's a last thing when all these fence instrumentation work, then it's more like a mechanical trip. So you can see already that we're all worried about the speed of the steam turbine. We want to control the speed because, as I said, if we don't control the speed, things can quickly go wrong. Is there any question on this on the previous component? Was I too quick with the component, or is okay? It's okay. Okay, now we look at the classification. I'll go through quickly. The turbines are classified general purpose, special purpose. I'll explain quickly what that means. Then we'll look at the number of stages, single stage, multi-stage. I'll cover through the concept why we have it like that. Then we got condensing, back pressure, extraction. I'll explain that. And then compounding, I will touch on that as well. And then the types of the governors, I will explain. And then we'll look at the impulse and the reaction blades. And then we'll cover and see what's the difference between and how an engineer decide which blade to use, which one not to use in a certain application. I keep using the word an engineer because my future, when I see all of you, I see our future Mohandis. This will be all relevant to you in your future. If you do well in your examination, I'm sure you will do well. Here, these are the things that will start helping you for your career decision as well, okay? We call it a steam turbine a general purpose for few reasons. General purpose in industry, sometimes we have an A, B, C pumps. It means we have 3 pumps for the same application, and they are designed the same. It means in that process, we have flexibility. If I want to do maintenance on the B pump, I can stop a B pump and start A, and then do maintenance and so forth. So I have a flexibility. So a general purpose steam turbine, they are very small. They do fit in where the equipment has a spare, ABC. Also, they are also constrained with pressure requirements. So the 48 bar, 400 degrees the temperature, the speed is 6,000 RPM. It's one of the requirements to limit the small or the general purpose steam turbine. Of course, the shaft or the power capabilities, the shaft power is some limitation. If you go to a special design turbine, they're very critical because they could be driving a compressor that does not have an A and a B compressor. So you only have one compressor, and this compressor is used in a very critical operation. You cannot afford to lose the compressor, and so that turbine, the design of that turbine, we need to make sure that it's well done, well covered, the reliability, and everything is in place so that you don't lose, because the operation, if you trip, you could easily then shut down or disrupt the operation. So then the turbine becomes very special for the operational reasons. And also for the design, the pressure envelope is not really limited. So the engineers have now flexibility to choose the speed, to choose the pressure. So they are not limited compared to the general purpose. In general, in industry, the moment we classify it as a special, it becomes a multi-stage turbine. And a lot of things that are quite important for reliability, they almost kick in. That's how we distinguish a general purpose and a special design steam turbine. We good so far? Anything I need to clarify? Okay. Let's give it a shot, let's engage. It's your turn now. Who want to give it a try? Why we use steam turbine? I'm worried my engineers are quiet. My future engineers are quiet. Yes, go ahead.
We have some sense of independency because with motors, if we have a power shutdown, we can't do anything. But here, we can't have the whole hand on it. We can't do anything. We're like independent.
So we are independent with the use of steam turbine. You want to elaborate a little bit what you mean in independent?
We can shut it down or turn it on if you want. But with electricity, if we have power shutdown, we can't do anything.
If we lose if there's an upset in the grid,
Yes.
so we can have a blackout. And then on a steam turbine,
We're independent. We can just turn
we
on.
have a flexibility.
Yes.
Okay, give him a chocolate. Oh, sorry, let's give others a chance. You want to go for it?
Okay, it has very high reliability and efficiency.
Excellent. You want to try as well, but I mean, I want you to speak up, but the chocolate goes to him now.
I already have none.
Okay. Okay, yeah, basically that's all about it. So in industry, for example, where we come from with our exposure, the refineries, the process itself by default in the refineries consume a lot of energy. Heat is available. So really they got the steam already available. Then engineers decide, well, using a steam turbine then almost become a very practical option. So it's a very flexible driver, especially when your process involves the steam. So then it's easy to design and use a steam turbine because you are already invested, you already have the steam in your process. And again, I like what he's saying. Normally, when you start up the refineries from a maintenance or a shutdown, we start all the machine that are steam turbine driven normally to get the refinery where it's required to be before you introduce gas or introduce feed. So these drivers, they always become a very good flexibility in the industry.
Do steam turbines have higher efficiency than gas turbines?
You want to hold the thought, we will get there. Maybe write down that question. Yes, a very good question. Okay, we are on the stages now. So single stage or multi-stage. That's how you can classify. There's limitation on the single stage. Normally it has one nozzle. Sometimes what we do, what you see here, we call it hand valves. So these valves on top of the control valve going to the steam, sometimes when you want to maximize a little bit more, is either we fully open these valves as well to let more steam or channel the steam more around the disc to get more torque so that we can fully utilize the steam. Really, a single stage is limited. It has one nozzle ring and it runs at high, the disc is high velocity, and you will see that later on. Why is it not really a good thing to expose? But general purpose, it saves the need. Then we come to the big boys, we call them multi-stage. We call them multi-stage because they are designed for high power, high efficiency and huge enthalpy drop. So later, if we talk about enthalpy drop, we will cover it. When we say huge enthalpy drop, means we maximize the energy. We sweat the steam, we consume that steam that the boiler provided. Then this guy is able then to deliver the torque that is required. How we deliver this efficiency, you now have a number of blades, so you are doing a lot of pressure, you do a pressure drop and you do all the velocity changes so that you make sure that the power from a turbine is really fully utilized. Later I'll get a little bit more clear multi-stage and all the blades into the turbine. But the picture you see on the right below, you start seeing big specialized steam turbine. So far so good? Is there anything else we need to, did it answer a little bit for now? You will see the calculations later, but you get the feel when we say how do we get a high efficiency on a steam turbine. Single stage again, these are just component. Again, I stress as a single stage turbine, we have one disc or one nozzle ring. We are limited with the torque. We are generating a torque required for that general or that specific need, but if we want to stretch it higher, we then require to consider multi-stage. I think I covered the component. I can recap if you still remember. This is a bearing housing. There's oil. We got seals. These sensors. This one could be a temperature on the bearing. So we are monitoring the bearing. The other one coming this angle, we could be looking for vibration. So there is some sensors other than just the speed. We can also try and monitor the vibration of the whole steam turbine. I'm not sure if there is. So you call this later on, I'll cover the reversing segment on the blades. This component helps you for the first blade that received the steam and transfer that profile again to the next blade. So that's why we call it the reversing segment. So it helps to transfer kinetic energy to the next blade. Is there anything maybe that I didn't cover here? I did say these are hand valves, or sometimes some turbines you have an option to put hand valves. So that's why you don't see that. But this is used to supplement, if you need to supplement and maximize the torque available by bringing more steam into the turbine. Is the hand up?
What is the nozzle with
Maybe because the pictures, I'll explain it later on. The nozzle, the only way to identify where it is, you see the steam enters here and it takes this direction to the turbine. So maybe there's another drawing coming there where you will see nicely how that nozzle ring sits in front of the disc, because it has to control and it has to channel the angle of the steam so you can strike the blades optimum to get your kinetic energy eventually when you need a torque. Is there a question, Shabab? Does somebody have a hand? Is all good so far? Okay, multi-stage, we've explained again, so you can see the shape of the turbine, tapering in. So I will explain all that, what's the secret behind the shape, but 1, 2, you can see now the blades, you can start getting a feel. What do we mean is a multi-stage? You can start getting a feel why it's called a multi-stage. What you see here and what you see here, it's the control valves. They are in the body of a turbine. I did explain. It's easy to control the steam. Also, the trip valve is mounted. We call it a chest, steam chest. It's also used so that when something goes wrong and we want to take action quickly, within a second we cut out the steam. You can imagine if there is a pipe, if this valve was in this position and we have to immediately stop the turbine, when we trip, there will be a steam trap between the turbine and the valve. So this steam will continue into the turbine. So when it continues, it has energy, it will continue spinning the turbine. And this is the last thing we want when the reason is now to stop the turbine. So that's why engineers mount it directly into the body of a turbine so that there is no volume of the steam available when you have to stop. Is that clear? Okay, any questions so far? We all good? Okay, it's your turn now, Shabab. Who wants to give it a shot? There's a question on the screen. Maybe I'm too quick. Try and observe what you see. Try and what you see. Can you see the difference? Do you see a difference, this and that? This is a blade, this is a blade. Do you see a difference? Let's see now if we can try and attempt the question. You want to clarify something before you see the question? Or you want to answer the question? Okay, good, go for it.
Because the pressure at the beginning is higher than at the end.
So why the blade is long? Yes, it's very good. The pressure inlet is higher than the pressure outlet. But why the blade at the end is long? Not far, not far. So you need to trust yourself. I think you got the concept. Why then that blade is longer? I wish I can give him half a chocolate, but I'm not allowed to cut the chocolate. Go for, give it a shot.
At the last stage, the pressure will be like a little, not compared to the beginning of the turbine. And if the pressure is low, it is harder to extract the energy. So
Okay.
you make the blade longer in order to extract the energy.
Yeah. Give it a try, the last one.
I think it's because of the volume of the steam expands, so we need to expand the chamber of the turbine.
Excellent. Please give, we'll limit 3 for now. Give 3 of them a chocolate. I'll explain why. All the words they've used, they're all correct. They understand that at the end of the turbine, the pressure is low, but we still want to go below the saturation line. You will see the enthalpy later on. So by increasing the length of the blade, we maintain the kinetic energy. So we still want that velocity so we can extract the maximum energy. So both of them, I think, they kind of like get the concept. So that's why I think they both deserve the chocolate. Okay, I will wrap up very quickly here. I'm just emphasizing the component on the multi-stage that you will find. You will find the seal, what you see, Labran seal. Again, very expensive commodity, high efficiency. We don't want to lose this. We don't want to lose the steam. So we use this seal to prevent any leakages. So if you want to see it more clear, the steam can go through at the top of the blade. It can leak through there. So the engineers came up with what is called a tip seal to minimize the leakages. The steam can go past at the shoulder of the rotor. So engineers came with called the shaft seal. All these function really is to enhance efficiency, that you don't lose energy. This is just another picture showing you how the rotor looks like. So this would be a casing, it will be a rotor. A casing now in the top position because it's an axial split. So the top casing, you can, when you close this parallel to the shaft and the line, I already covered what you have, which will be clear later on. We have what we call diaphragms. You can think of diaphragm as the divider. There would be one rotating blade here, there will be two diaphragm, one blade here. We call it blade or blade carrier. So you will see the next picture. This is a stationary blade. These are rotating blade. They have that profile. That profile engineers came up with is for all aerodynamic purposes and the efficiency of the converting kinetic energy to the torque. This is a diaphragm, so this is another picture. So what I was trying to explain, these components are called diaphragm as compartment. They are not rotating, they are stationary. They support bending moment or bending stresses. They support the rotor. They got diaphragm rings to channel the profile of the steam to the blade. That's basically what their function is, to house those rotating blades. If you make a mistake on installation, one of them is turning and is touching the diaphragm, that could be a disaster on the machine. You can destroy the turbine. And this one was just trying to show you. So the yellow and the gray is not rotating, stationary, 0 RPM. This color is a blade. That's the one that is most of the time seen as centrifugal forces or torsional stresses, whatever engineer you need to worry about. So this is basically trying to show you how this in the cross section can look like. And you remember we asked why that blade is longer at the low pressure side of the turbine. So far so good. Let me cover the important component as well. We mentioned that in the chest of the turbine we need to control the load. We use this valve to regulate the steam. There is a sequence how we can tell the control logic which valve number, which rack number you need to fully open, which one you need to hold 50% open, because we are now playing with the load, because we want to meet the demand. So that's how really the steam control valves work. They work like a camshaft of your car. So that's how they sit like on the chest of the turbine. So they load control purposes. This guy is the guy that is either is happy, is open, or somebody tells him take an action now. When he takes an action, you blink your eyes, the steam is closed. This is the function of this valve. We call it emergency stop valve. So far, so good. Okay, just Shabab, remind me with technology. Which of the following describe a single stage steam turbine? We want to give it a go. Which answer I should select? Who want to give it a go? Yeah?
C.
C is the answer. Oh, I need to go there. Anybody else want to give it a go? I did cover single stage, multi-stage. Who want to give it a try? Which of these define a single stage steam turbine? Okay, give it a go, yeah? D. Oh, sorry. I keep wanting to go there. Excellent. Give him a chocolate. One nozzle ring, two rotating discs, the one I showed in the picture, and the reversing, transferring the steam to the next row. Okay, you want to give it a try? I've talked about the seal. Steam is very expensive. We don't want to lose it. You want to contain it to the turbine. So the seals are very important. Who can give it a go? Which one do you think here are the seals used in the steam turbine? Yeah, go ahead. D. Want to give it a try as well? Yeah, go for it.
B.
B. Yeah. One chocolate. Who else want to give it a try? Yes?
A.
A. The noise was, but these are two the correct answers. Give them chocolate. Okay. How are we doing, Shabab, with time? Is okay? The pace is a little bit slow. Let me know when I need to. Okay, we talk about the blading. So we're looking at now impulse turbine blading and the reaction type. So very quickly, if you look at the picture on the left, what you see here is you are seeing a nozzle. This nozzle, we use it to drop the pressure. We want to drop the pressure so that we can get the kinetic energy. If you look at the graph, this nozzle, look at how much is the pressure is dropping, and watch what the velocity is doing when we hit the blade. This, what you're seeing is half mv squared, yeah? Half mv squared, that's what we're looking for, so that we can have a torque. So this type of a turbine, the only pressure drop happens here. This is the only component that is designed and used to break the pressure, so we can get them. You can see right at the end, as you go in the stages, then the pressure sort of remains constant. Now let's turn the focus on the next picture on the right. You can see this is a fixed segment, it's not rotating, this one is rotating, and you can already see the profile is not the same, but you can also use this drawing. So you see we have a pressure drop before we enter this blade, but this you cannot compare with this. You can start seeing the difference. And you have a velocity going high, but you cannot compare with the left-hand side. But you can see they start complementing, meaning they are sharing the pressure drop. The reason the engineers call it reaction is the drop happened on both components, and it's kind of like 50-50 pressure drop. Then they came up with the wet reaction turbine. When we go deeper into design, one of the disadvantages of this turbine as well is it tends to introduce a lot of thrust or axial forces. In big turbine, you will see that they even design balancing drum or balancing piston to manage or cancel out the thrust forces. So it has some design challenges. Also, in a very special purpose, these two design, this concept, the engineer can combine them in one turbine to meet a specific design goal. So you are able to have a blade that little bit looks like an impulse, and then as you go deeper to the turbine, you can play around with the blading arrangement depending on the application. Any question on the blading?
What's the difference between them when I choose what situation?
So in general, single stage, for your information, we stick with the impulse. You'll see later on the next slide, which will answer your question a little bit more. But the low pressure application, low horsepower, normally you purely stick to you can stick to the impulse. Let me show you why you will do that. Okay, I will finish this. I have a table where I list the differences between the impulse and the reaction. But as I explained before, you can see the profile of this. You break the pressure on the nozzle. All we need here is really the high kinetic energy. So we don't break the pressure further, we break it once through the nozzle. Okay? This is a reaction. You can start seeing the difference quickly, show you. Look at this shape and look at the next shape. Look at the blade, and you look at this blade. Can you see the difference? You see the reaction is a little bit different, and all what the reaction it does is it shares the pressure loss, the pressure breakdown. So between the rotating element, there is a minimum pressure drop. Between the stationary component, there will be a pressure drop. But you will not see that on a pure impulse turbine. The pressure drop will only happen on the nozzle. Okay? Give you some time to see. I can move on if there's no question. Okay, he asked a very good question. When as an engineer, he can decide whether just use the impulse. So pressure drop on the nozzle. Another thing that, because it's general purpose, really the efficiency might not be that important. It's a small power output. And also I'm looking for the cost. So to manufacture that profile, design and build and make that blade is not expensive. Compare when you have to design the blade for a reaction turbine, because with the aerodynamics of that blade, you need to take note that you want to minimize the thrust forces on the steam turbine. So really you want to break the pressure 50-50 in rotating component and stationary, but you're also mindful the thrust forces that can be generated by the reaction turbine. So that's why coming up with the blade on the reaction turbine is a little bit an involved design process. Any questions so far? Okay. Okay. Which of the following is not a type of a steam turbine? Who want to give it a go? There are things written here. Some of them we are saying it is not related to a steam turbine. I need to distribute the chocolate in the right sequence, right? I start, the gentleman on the right on the top. Yes, go ahead, give it a try. B. B for Becky, eh? Let's try B. Who else? Right at the top, the gentleman in the navy t-shirt. D. Let's give it a try. Why I like D? Do I also know something about D? Okay, give him a chocolate. Thank you very much. Okay. All right. According to how we exhaust the low pressure steam, when we say exhaust in a steam turbine, we are already talking about a very low steam pressure. When we say high pressure, you will hear the engineers in the field say HP side means it's high pressure, LP is low pressure. So I'm just showing you an example of 3 turbines. Some turbines, especially in the power generation industry, the way they use the steam and they extract the steam could be a little bit different. But the common one is the condensing type of the turbine. You saw it on the ramping cycle. We extract the enthalpy. When we are done with the work and we avail the torque, we then drop the heat sink on the condenser. We then return the steam to the boiler. Then it's a closed loop. The other type of a turbine, it has its disadvantages. It's a back pressure turbine. Back pressure turbine is that line you see on the HS curve. It tends to discharge the steam, and the steam still has that energy that we're looking to extract. So it's not really a very efficient steam turbine, but it does not mean it's not a common turbine. Compressor drive is a normal turbine that you will find in the refinery. But the reason in the refinery is the steam requirement sometimes is different. You've got heating processes, you've got dumping station required. So sometimes the back pressure turbine finds its place. But when we really want to maximize the steam energy or efficiency, he normally becomes the candidate because he then has a full enthalpy drop. He dropped the pressure below atmospheric. That means we really extracted all the energy from the steam. This one you can also find, but it's not common in the refinery where you have to have a high pressure somewhere in the stage. You want to extract the steam that still has an energy because maybe we want to heat something else in the process with the steam. We call it we have extracted steam. So it's an extraction and then we still continue to exhaust to a condenser. So again, an engineer to come up with it means there is a process requirement that maybe in this steam turbine I can get the steam still at the high pressure and use it for a process need, but I have not compromised the torque that is required for the primary function. So this is a range I can share. They are all applicable. They all got their needs in the industry. They are just basically a design decision, an engineer and the process requirement. Any question yet? As I said, nothing would be strange. In the thermofluid, you have now had the word condensing turbine. You've had the word extraction turbine. Also, when you do when you do performance and you analyze them, the approach in enthalpy is the same, but you need to be very careful with the parameters, how you group the parameters to work out efficiencies. I'll show you later on.
Isn't the back pressure steam turbine, the line goes to a condenser, the same like the condensing steam turbine?
The reason we call it a back pressure, we discharge the steam at the high pressure. So we cannot have a condenser. A condenser is more like this heat exchanger is designed for vacuum purposes. So now I cannot have a pressure into that heat exchanger that is high, because then I could easily limit the pressure capability of a condenser, also for cooling purposes or condensing purposes. So that pressure, the steam with the energy will go to somewhere else. So where basically I used to work, we will take the steam to the drop-down valve or breakdown valve stations, because they need that energy on the steam. But you should never think of a condenser here. When you see a back pressure turbine, or when someone tell you that one is a back pressure, you know there is no condenser. You already know we're discharging the pressure, we're releasing pressure still with high energy content. So that's why I'm saying it's not really an economical, but it has its own place in the process industry. So far so good with exhaust classification of steam turbine. Any questions? Is it adding up? Do you remember anything in the book? Can you relate now? Is it helping?
In the right extraction steam turbines, one of the lines goes to a condenser.
Yes. So this one, as I said, it could be numbered blade number 3 on the multi-stage. You could decide, an engineer, I want to extract the steam on blade number 3 because the pressure on blade number 3 is still very high. So I can get that heat content and use it somewhere else. But you are not saying I cannot continue to perform a function that look like this. So post blade number 3, we can continue breaking the steam and we can condense and then the loop again, and then it becomes a closed loop. So it's a good question, yes. Okay, is there a question on we're good? So then we have different types of governors. I talk about the governor. So the best way to explain to a future engineer what's a governor, I can explain it in this concept. When you drive your car and you go uphill, when the car goes uphill, do you press the pedal, or you don't press? If you don't press, what will happen? Who can answer this question? Now you are driving your car up the hill. Now you lift your foot off the accelerator. Will that car go over the hill? Why cannot go over the hill? Yeah?
Because we have the gravity, we have nothing to react to it,
So there's something resisting the car to go over the hill. But if you press the pedal, you will be able to go over the hill. Now you're going down the hill. Do you need to press the pedal, or you need to pull your foot off the pedal? Now you're going downhill. Imagine now the car is going downhill. What will you do? Will you press hard on the pedal, or you take your foot off the pedal? Why are you taking it off the pedal? It's because you are uncomfortable. It feels like the car is running away. It feels like you as a driver, you are no longer in control. Then your foot will immediately move into the brake. This is how I can quickly explain what's the function of a governor in a steam turbine. The governor helps us to control the load of the turbine, also to control the speed of the turbine. So if we need X amount of the speed, the governor also helps us then to regulate the speed. It's really a device that is used to regulate the speed of the turbine. That's why I use the car as an example. So the old days, there was a mechanical one. It works on a centrifugal force. When the turbine is spinning, these weights, when they stretch apart, it means the speed of the turbine is too high. When they spread apart, they push this lever down. When that goes down, it will hit a trip pin on the governor, then it will trip the turbine. That's how the mechanical governor used to work. Then engineers, the technology improved. Then we came to a governor, it's called now hydraulics. So we make use of the hydraulic to control the opening and the operation of the governor. So all technology, that's the medium, is still common on general purpose steam turbine. You can still find a hydraulic governor, but really on critical and special purpose turbine, this one is more reliable because it works now on the intelligence of the control and the management of the speed of the turbine. And it's not only this one, there's more in the market already available, but these are the common, and in turbines, the electronic tends to take more, engineers tend to favor especially in a special purpose turbine and a critical application, because you don't want a mistake when you make a call to cut the turbine. You need to know your speed very well. Any question on the governors? Okay. Good. Somebody's turn now to engage. The electronic governor is more accurate than a mechanical governor. Let's try and distribute the chocolate again. The gentleman on the top, a white t-shirt. What's the answer?
B.
B. Okay, give him a chocolate. That's true. As I said, technology, algorithms to control the speed with the sensors is quite important. So that governor becomes more accurate than the mechanical or design governors. Okay, we are now in the stuff that you now need to teach me. So I won't spend a lot of time. I'll learn from you because I don't know how long I've left the academic, but again, this is very important. Why I'm having this with you today is because in the industry, I still use this. When I have a task as an engineer to work out the steam turbine efficiency, if I don't know this, I will be making a lot of mistakes when I do the calculation. So this is very important, but you will help me, we go through quickly. So when the steam goes into a turbine, it has a state one. State one could be a function of P1 from the boiler, T1 from the boiler. We take those parameters, they become an input into the steam turbine. So we know now, we all know now that enthalpy is a function of these two parameters, that's correct? So how will I get the enthalpy? Who want to take a 1 second guess? If I need to know the enthalpy, the specific energy on that steam, and I know the boiler pressure, and I know the temperature that left the boiler, how will I calculate H1? Who want to give it a guess? Okay, he's going to take all the chocolates, Shabab, if we don't try. Yeah, the gentleman at the top, yeah.
We use the tables.
Okay.
We know the superheated.
Yeah, speak, you're coming right. You have a very good concept.
Yes, we know the pressure and the temperature. We can't find the enthalpy.
Excellent. So he's saying is we know P1, we know T1. On a steam table, we can go define this and use H1. How will we know is we should go to a superheated region? How will we know we should go to a superheated? How will we test that? The gentleman at the top, yes? Yes?
If you are above the saturation temperature, it will be superheated.
Okay. Take note of what he just said. He make a very interesting rule. T said, so if we are like this, that T1, if T1 is higher than this, we cannot be in the saturation. We have to be in the superheated region. Is that what you're saying? Give him a chocolate. So keep in mind. And then H2, how will we calculate H2? We want to give it a guess. Now, the steam, maybe before we go to H2, can you remind me what is this line called? What is this line? And why is it straight? So you will get 2 chocolates if you can answer me. What is it and why is it straight? This side is taking a lot of chocolate, so I want to avoid it. I want to distribute the chocolate. Yes, go ahead, sir.
Straight because there is a path.
This line, from this dot all the way to S1, you're saying straight because?
There is a path.
There is a valve. What is the valve doing?
Increasing the enthalpy.
The valve is decreasing the enthalpy. Hold the thought, let's give it a go.
This is an isotropic process when we have the entropic process.
Isentropic. Very good. And what is isentropic? What do we mean by isentropic? Who want to supplement him? He will get the chocolate. He has a good answer. Who want to supplement and support him? Why is it called isentropic?
No work.
Sorry?
There is no work.
Excellent. So there is no heat transfer. The process are adiabatic, right? So give them both chocolate, right? So that's how the advantages of this. It then sets up very quickly to work out this isentropic enthalpy. But let's just remember, in the real world, the steam don't do this. The steam do this. Because inside the turbine, there's friction, losses. So this concept here now, it's a reality. This is a real in the turbine, in the steam turbine. But the good news is we then make a rule and say that pressure is the same. So in other words, this actual enthalpy has to stay on this pressure line, right? Now, if it stays in this pressure line, how will we calculate H2? This section is very important because we're going to do the calculation. How are we doing with time? Are we doing okay with time? You want to give it a go again? How we can calculate H2?
The pressure of the concept of between the isotropic process and actual okay.
Yeah, we are on P2, yeah. Here is H2. How we can quantify this?
Yeah, as we can actually know the P2.
Yeah, we know the P2 and when we agree that P2 is this the line, and we agree that whatever the pressure is there, they all on the same pressure. But it's something, because this is a real expansion in the turbine, we don't know this, we need to, and you can see it's higher than this. This energy is higher than this. So how we can quantify this? Gentlemen, right from the top.
Use the isentropic efficiency.
Use the isentropic efficiency. How will you use isentropic efficiency?
By dividing H2S.
To find this value.
Yes.
We will not have isentropic efficiency without this value. This value we needed to calculate isentropic efficiency. So to find this value, we normally give in the turbine, we know the exhaust temperature, we know the exhaust pressure. Those two parameters, P2 and T2, they're not applicable here. You'll be making a mistake to use T2 to define this point. That T2 and we are given on the turbine is for the actual expansion. Never take that value and put it here and try to define this. The P2 and the T2 are the parameters to help us go find H2. Once we found H2, we are then able to calculate efficiency because we now got all the enthalpies. So H1 minus H2, H1 minus H2S, that can give us now a turbine isentropic efficiency. Good? It's important to remember this. And then, of course, as I said, this line, if we really land in this range, it means we have taken the energy from the steam. We do have an efficient turbine. We extract the energy. Any question here? But I mean, this is your area of comfort. I don't have maybe to spend time here. It's just to refresh, because later we're going to work together on the calculation. Okay. So we have an example. Because of the time, we don't have to calculate in detail. It's just an interaction. We have an example. You are an engineer. It's a back pressure turbine. Let's go very quickly. You are being asked to define the inlet parameters and define the exit parameters and tell somebody what is the efficiency of this turbine. And somebody wants to have a compressor. He wants to know from you whether this shaft, this torque is suitable to drive this specific compressor. How will we start? We now know that the inlet pressure is 4,000. We know the inlet temperature is 400. What we can quickly find with these parameters? While I draw, someone can help me give me the answer.
Find the enthalpy.
Sorry?
Find the enthalpy.
We can find the enthalpy. Okay? Let's say this is our P1. This is our P2. State 2, state 1. This is our asymptotic. So this is our HS. But here is a real world of a steam turbine. So this is our H2. Now we are being asked to define this point in the compressor. How can we quickly find this? So how can I go up? But I have a steam table here at 400. The temperature is 400. The pressure is 4,000. What should I do quickly? Here's the steam table. Who can help me quickly to go through this? We want to give it a try. We should be within 2 minutes for this because we all got thermofluid exposure, right? We should go through it quickly. So we know the temperature and we compared. You remember this rule? Did I erase it? No. He made a very good rule. T set and T1. Our temperature is 400 degrees at that pressure. And this pressure is here. So that's 4. That is same as the 4,000. How can I find H1? What is H1? It's right here. We have an exercise later. I just wanted to use it to engage them quickly so they can refresh. Anyone want to give me quickly, what's the enthalpy? Yes, go ahead.
3,240.
3,240. Very good. So we have H1. So H1, can someone write for me? I need to be very efficient with time. I'm mindful with time. So keep that number in mind. So we have H1, 3,000. So how did we find H1? 400 was the temperature inlet from the boiler. And the gentleman knew that this is the saturation temperature at this pressure. Then he quickly checked, that temperature is lower than 400. Then he knows, okay, this must be a superheated steam table. So that's how he identified the H1, okay? Very good, this is the right concept. So we are close. We now know H1 of the steam coming in. How can we find the variable for the steam coming out? So we need H2S, we need P2, then from there we can calculate the efficiency. We are given the mass flow rate. They told us upstream inlet and outlet is the same, so we can use that to calculate the power later on. But before the power, we need some variables we need with these conditions. And these conditions are on the P2 pressure line. How can we find from P2? Yes, go ahead.
Don't we need another table?
Very good. So what is that table? Help us, all of us. Why do we need another table? You are not fair with me. I've already given you a table. Why you don't like this table? There's a good reason why you want another table, and I want them to learn why we need another table. Yeah, explain for us.
Because the pressure is different from the pressure the table given.
Okay, good. So what do you think? You think we need a superheated or we need a saturated region? By looking at what's the discharge pressure from the turbine, or what's the exhaust pressure? You think it's saturated? Sorry? Okay. So let me see if I don't have the steam table, but we can just go through it and explain. I'll explain it to you. Then you will do the calculation, the next one. Is that okay? I can go through it quickly. So what we'll do is, if we need H2S, we want to use the S, because we said that line was isentropic. So we need to quickly say S1 has to be the same as S2, isentropic. So we now know we have S1, so we can read S1, so this is our S1, but that's not enough to calculate H2S. Now, something else we need. If we go to the saturated and the temperature at this pressure is higher than this temperature or lower than this, it means we can't be in saturated, we're in the superheated region. So we still need to go to a superheated steam table, but for this pressure, to go and identify the entropy at the saturation, so that we can calculate X. See if I did bring the equation to calculate X, just to remind you. I didn't. I think I can go back. Did I show you how you work out X? No, I didn't. Okay, so to define S, we have the S, we will say S minus SF, that's saturating. We will divide it by evaporating entropy, SFG. That will give us the X. Why we need the X, we will then go to a normal saturated to read the enthalpy for the liquid. So HF, we get the HF, and we get the HFG, and then we have the X, we then calculate the H2S. And then we need H2, then these parameters are the actual expansion, so we can use the pressure in T2 to get the H2, not the H2 isentropic, the actual H2. Once we have that, we can plug it on the equation and calculate the efficiency. Once we have those enthalpy, we can now, we've been told there is a steam mass flow, so we can calculate the power. Because the power is m dot delta enthalpy, so that will give us the power of the turbine. This is really a concept how you will do the efficiency of the turbine by using these thermodynamics principles. So far, so good. I just wanted to, the intent at the beginning was to go in detail with you, but I thought for the sake of time, we can still deliver the concept, how the whole thing works. And later on you can check it and you can verify all the answers you are able to solve it. So I've given you a receipt how to solve it. And I'm sure you're familiar with it, okay? We had prepared a very quick assignment, and I already worked out a lot of figures for you. It should be quicker for you to do this so that you can have a chocolate. So we have 10 minutes. So we'll make it like 6 minutes. The one who can finish it quickly will have a chocolate. Again, as an engineer and you're learning principles, don't dwell too much to the right answer. Somebody, when he used to teach me, he says, when you start understanding the principle and you apply them correctly, by automatic you start getting the correct answers. But when you chase the correct answers and you don't grasp the fundamental, you will always lag behind. You can support me on that. You can support me on that. Okay? Do you wanna give it a shot quickly? so that whoever get the answer first, we give him the chocolate. So maybe I explain what has been given on the turbine. Okay, it's the same turbine laser sketch. We've been told the inlet condition is a 3 MPa, that's a boiler pressure. We've been given the temperature from the boiler, the steam to the turbine, and we are given the exhaust pressure 50 and the exhaust temperature. We are being asked again to do performance of this turbine and work out the efficiency. Is it the efficiency this time? Where is the question? See? Yeah, sorry, it is an efficiency and the mass flow rate. The other one before was the mass flow and efficiency. Why this one is the mass flow rate? Because fortunately we know what's the shaft power. So the power is, we know, it's a known quantity. What we don't know, how much steam should the boiler then provide to the turbine? Somebody want to give it a try. If something not clear on the given parameters, let me know. I'll shout them for you quickly so you can just flow with your calculations. I try to bring the enthalpy to see if they can help you. Saturated I have, superheated I have, and if there's something missing for, you can also quickly make an assumption. So long as an engineering assumption, very good assumption, close to your knowledge of thermodynamics, we can give you the chocolate. We're not marking wrong or right answers, we're searching for the concept, the fundamentals. So timekeeper, you will help me. If we run out of our 8 minutes for the exercise, just raise your hand so we can then move on, so we stay within the allowable time to respect the evening. Again, while you're calculating and you're thinking why the Aramco engineer is showing us this, all I'm reiterating is the fundamental. How important for the engineer to understand this information. Many machinery engineers struggle to understand the concept of a saturation temperature, superheated temperature. That's why on heat transfer calculation and efficiency calculation, it becomes a game for them, because this is what they miss from the beginning. They miss the foundation. Help me to zoom. They want to zoom in? Yes. I can read it as well, the parameter, if there's something they want to see. Is there someone close to an answer?
Regarding the first state, it has X while it's superheated. Does it make sense?
It has X while it's superheated. Explain to all of us, what do you mean it has X while it's superheated?
X means it's saturated.
Can we all see? So you're not happy that you're getting X before you even go past the saturating line?
I'm past the saturation line. Why I have X?
Yeah, you are in the wet region.
The superheated region.
You are in the superheated region.
Yeah, first state.
The inlet to the turbine from a boiler. Where is the parameters? If you went down, from the boiler you got 3,000 kPa, you got 400 degrees. You're saying you're getting X in this inlet condition from a boiler. This is superheated region.
Yeah, so I shouldn't have X.
You shouldn't have X.
So why there is X?
Or no, X is a number, sorry. Now I understand the question. I've calculated that for all of you. So when you go to the wet region and you're looking for X, don't stress, I already worked it out for you. I just wanted to speed up the assignment. But that X is not related to inlet conditions.
Yes, it's X2.
It's not X, it's the X for the exhaust conditions. So when I was preparing the data, I should have moved this X to these conditions, because it's not related to these two parameters. These are high pressure, high temperature, straight from the boiler. Should never have X. Oh, you gave me a fright, I almost. This is high pressure from the boiler. It should be still up there on the superheated region. He's correct. I mean, I confused him where I placed. X is already calculated for you. You can just plug that number and we quickly discuss the solution. So all the other parameters, I quickly went through them to speed up the assignment. You should give me a chocolate as well. All right, I think Shabab, we're doing well. Is there anyone want to explain even 2 or 3 steps that you attempted it? even upstream of the turbine, P1 and T1, you already defined something you want to share with us? What was your H1? This is quite, you get points for this. What was your H1?
H1 was 3,230.
You also got the same? H1? He had 3,230, right? What did you get, H1? He can't see the superheater. Let me read it for him. The inlet pressure is 400 from the boiler. Okay? The pressure is 3,000 kPa or 3 MPa. So the enthalpy is here. Search now what is H1 from 400 and the 3,000 pressure from the boiler. You can quickly read now what would be the H1. Anybody manage to find H2? You find H2?
Yes.
Share with the team, how did you find it?
F plus X, F.
That gives you H2. So it gives you this value.
Yes.
And you use X. Okay, hold the thought. Who want to comment what he's saying? He's saying, I have found the actual enthalpy for expansion in the turbine, but I use the dryness fraction and the wetness of the steam. Is he correct?
He found H2S actually.
That's what he meant. You have found this point. Very good. And you use the dryness factor to find this isentropic enthalpy. Okay, he deserves a chocolate, and him with the H1, we can give them a chocolate. Let's wrap up because of the time. Really, it's not to test you how much you know. I need to be very clear. It was just for all of us to recap on the fundamental, the importance of applying these properties to work out the steam turbine efficiency. I'll show you now the solution quickly. So here's the solution. This is what you should have got as an engineer when you tackle this job. This is what should be in your engineering report. I've done the turbine calculation. This is what I found. There is a mass flow rate. These are my parameters. And this was asked because you already knew what was the shaft power available. We can take it further from here. We can say, let's select the blading, but that is too deep for you now because we can now use this. We can use the rotating speed of the turbine. We can work out the tangential velocity of the turbine, and we can start playing with the kinetic energy to see which blade, which profile will meet our need. But it's a little bit deep. I won't cover this today with you. It's just to give you that you can expand a little bit further once you've done your thermodynamics. This is the foundation for steam turbines. Any engineer misses this, is game over. He will struggle. You will struggle a lot if you cannot understand this. No matter now how I think I talked to him before, I said, what I wish for you in the future is what we struggle is, let me just go back. Sorry, I might be in trouble with time here, but I'm also passionate with the subject. So what you find in industry, there's 10 blades inside. It's a 10-stage turbine. But what we do in industry, we take that point, and that point, we then report a turbine efficiency. It's actually not correct. We should come up with a tool where each segment inside the turbine, we are able to quantify the efficiency on each stage, then we have an overall stage. So these tools in industry are still scarce, and I'm looking upon you that you are coming, joining us. You will start coming up with this intelligence, how you look at the turbine internally to work out the actual efficiency of the turbine. This is one homework I can give you to you about tonight. Okay, there's a question now. It's your turn again. Who wants to give me the shot for chocolate? Let's see if I did distribute the chocolate correctly. Let's give him a chance. Excellent. Water droplets, he's saying it might be a mechanical integrity issue with the blades. Give him chocolate. Okay? You will see later on why his answer is correct. I have some pictures. Yeah, he just said now, he talks about water. So this one is not water, something that shouldn't be, that was not supposed to be inside the turbine. It finds its way into the turbine, and this is the damage it causes to the blades of the turbine. We call it foreign object. to link what the good answer you just said now, water, high velocity, you can imagine, you can tend to erode the blades. It's not that the turbine cannot work. Again, you start seeing a performance of a steam turbine decline. That's how engineers make a judgment and say, why is that performance declining? Are we having liquid now into the steam? So when you're an engineer, you're monitoring the steam turbine parameters, you need to always ask yourself, when you develop your tools to monitor the turbine, from a boiler to the turbine, your eyes don't move away from these parameters, because when T1 drops to below a saturating temperature, you need to tell the operator, we are now not getting steam into the machine, we're getting water into the machine. Somebody had a hand when I was explaining the, let's go back to the pictures, sorry. So I'm just showing you typical challenges now in the field. This is what we deal with in the field. Steam quality is very important. Siemens, GE, when they design a turbine, they will tell you straight away. You can open their manual. That's where they talk about steam quality. When you have a new steam turbine, you are commissioning it, the first step to introduce it into the operation, we have to do what you call steam blowing. Steam blowing, we are cleaning the process from the boiler. We are cleaning all the pipes from the boiler, but we bypass the turbine. We don't take that steam through the turbine, because if we do, this is a damage we can cause on the brand new turbine before you even start it. So we do steam blowing. It's an engineering or international standard to do steam blowing, to clean the steam. Siemens or GE, they will have something called a target blade, where every time the steam with a high velocity pass that blade, when we stop a blow cycle, we pull the blade, we inspect the blade, we agree that the impingement in the blade, they are not this size, they are not visible with our eyes. If it's still visible, you fail the blowing, we repeat the blowing. Why? Because there's money invested in a steam turbine. You don't want to damage a steam turbine, right? So these are the things that in industry, we all, when you join us, we all face, that you need to make sure your steam quality. That's one aspect. The other aspect is the steam quality in terms of chemical treatment. It's very important, because when the blades start having silica or conductivity, when it starts becoming high, you're scaling up, you're building fouling on the blade, your efficiency of the turbine drop. Then the compressor guy complained, I can't get the flow rate through the compressor. What is wrong with this turbine? In the meantime, somebody who's responsible to take sample, treat the water, treat the steam, make sure the steam is correct, so then the turbine can deliver the torque that the gentleman told us. You need the torque from the steam turbine. Huh? So these are the things that in industry, when you join us, these are the lubrication for the bearing, the quality of the oil, you've got forces, you've got the high speed, the quality of your oil is important, because when the oil is not clean, without vibration, you can also, with particles, you can rub the bottom of the bearing, because the shaft is on the top, you can now scratch the shaft and you can damage the bearing. Also, when you have vibration and you're not controlling vibration because you have water or moisture in your steam, or your steam setup is not correct, your journal can end up damaging, you can end up damaging the sacrifice layer called babbitt on the bearing, and then you're having issues with the turbine and bearings. These are the challenges in the field that we try and deal with day to day. Steam turbine we tend not to use, not a better question, but we tend to stay away from the word cavitation, because we look at it in this way. So the steam, if it has water, we don't call it cavitation, we call it liquid impingement on the blades. We don't really look at it from a point of flashing out. So that's why sometimes the word cavitation is not a quite word when you're defining a liquid carryover into the turbine. So it's not a bad question, it's a good question. Anybody else want to check in? These are it's not all we've covered today is far from the whole complete knowledge of the steam turbine, but the intent was to start, we go together with the basics and the fundamental and start relating in your career. I would like these challenges. I've already given you one challenge. How do we work out an efficiency of a turbine on each stage? Not to oversimplify and say inlet and outlet and you define an efficiency. We're still looking for someone who can bring this intelligence to the industry. I'm looking at you, inshallah. This is you coming in the future helping us. Good? Okay, very quickly, is to give you an idea when you walk in the plant, you're an engineer, this is a layout of the turbine. The important thing we want to do, we're trying to do really high quality pictures. This is a loop wall system. Here's your turbine on the top. We use the oil for the lift of the bearing, the shaft to support the turbine for, for the hydraulic forces. So the loop wall skid, we use that. This is a generator drive, this is your turbine, this is a gearbox. Sometimes it could be where the torque or the speed here could be higher than what this guy require. If this guy require what we can produce here, we then bring a gearbox for reduction, we bring it down, then we give him the speed that he wants. Normally, for electricity generation, he normally 60 hertz, he requires 3,600. This is how the power plants, the generators work. So sometimes we do that, we bring the gearbox. All what you see around, these are auxiliaries to support the equipment. So we thought, let's show you a skid when you're on site, how's the layout of a steam turbine. Always on the top, on the foundation, and the loop oil, you will find them on the bottom. Good? Thank you very much. I hope I've tried to engage you, I've tried to give you a flavor. It's impossible to give you everything about steam turbine, but I needed to share with you fundamental foundation, what is lying ahead of you. This was really my intent this evening, to engage with you and we exchange this knowledge. Thank you very much for your time. It was a pleasure.
We have now come to the end of our presentation. I would like to thank you all for coming, and before we conclude the seminar today, we would like Turkish Shahrani, KPBM Azmi Student Section Chairman, and President of Mechanical Club, Ramzi Ramji, to hand the certificate to Mr. Bouquet for this report for today's seminar.
Thank you very much. Thank you. Thank you. Thank you very much. Thank you. Thank you very much.
Thank you for everyone again for attending the seminar today. And now we conclude with a group photo. صورة جماعية.
Thank you very much.
شباب التقييم عشان تحسب الأنشطة غير التدمير. ما حد ينسى ها؟
خلاص
فيصل في